Hi everyone, welcome and thank you for joining us today for the conference of Professor Nora Noffke. We have just finished the first course in geobiology here in Argentina, so this conference represents a great closing for us all. I would like to thank Nora for her participation today, since I learned a lot with her dozen of papers and her book. She has been very influential in the scientific community and for me in particular, especially when I started my own studies in geobiology, and I'm sure for most of our course participants as well. So naturally, I am honored to be counting with Nora's participation. Now Jerónimo will briefly list Dr. Noffke's academic background to then continue with her talk. Again, thank you so much, Nora, to be here in Argentina, at least by Zoom. Thank you very much.
La profesora Nora Noffke es una profesora del Departamento de los Océanos y Ciencias de la Tierra en la Universidad Old Dominion de Virginia, en Estados Unidos. Su especialidad es la sedimentología, es una sedimentóloga y se especializa en la influencia de biofilms en ambientes sedimentarios clásticos. Ha trabajado sobre todo en planicies de marea del Mar del Norte, en Alemania, y en Egipto, y su concentración principal es cómo los biofilms contribuyen a la formación de estructuras sedimentarias. Ella, con otros colegas, ha sido quien acuñó el término MISS o MIS para Microbially Induced Sedimentary Structures, lo que nosotros conocemos como las estructuras sedimentarias de influencia microbiana. Estas estructuras pueden llegar a tener hasta una edad de 3.5 gigaaños de antigüedad y sirven para contribuir a la reconstrucción de paleoambientes y paleoclimas. Inclusive se las ha tomado como posibles análogos de biomarkers para la exploración de litologías clásticas en el planeta Marte. Rápidamente, la doctora Noffke obtuvo su magíster en ciencias en el año 92, en geología y paleontología por la Universidad de Tübingen, en Alemania. En el año 1997 obtuvo su PhD, su doctorado en geomicrobiología en la Universidad de Oldenburg, en Alemania también. Después hizo un postdoc en la Universidad de Harvard, en el grupo de trabajo de Andy Knoll. Y desde el año 2001 hasta la fecha es profesora en Old Dominion University, como les dije, en el estado de Virginia. Y desde el año 2003 está afiliada a la Carnegie Institution de Washington, D.C. Entre los reconocimientos que ha obtenido es el de ser miembro de la American Association for the Advancement of Science. Así que, bueno, les quiero comentar que pueden ir haciendo preguntas, por favor formúlenlas por escrito en el chat de Zoom. Al final de la conferencia yo las voy a traducir, si quieren hacerlas en castellano, yo las traduzco, si no háganlas en inglés, y bueno, las va a contestar Nora al final de la charla. Por favor resérvenlas para el final. Bueno, muchas gracias por estar todos participando. Nora, I just gave your introduction, so please go ahead with your talk. Thank you very much.
Yeah, thank you everybody for being here. I hope you can hear me very well. And so the topic of my talk is turbulent lifestyle, benthic cyanobacteria on Earth's sandy beaches today and 3 billion years ago. Up. Here we go. Let me start with a very bold hypothesis. I say cyanobacteria are at least 2.9 billion years around. So, as you know, there is the discussion about how old are cyanobacteria, when do they come up in the fossil record, And so there are certain sedimentary structures or fossil that suggest cyanobacteria are around already in the Archean. And this is kind of my contribution to that discussion. So in modern tidal flats, we know that cyanobacteria, together with a lot of other microbial groups, form microbial mats and biofilms, and those microbentic communities interact with sediments and form microbially induced sedimentary structures, which are abbreviated as MISS. Now, those MISS occur also in the fossil record, and we know them very well from tidal flats simply because we can study modern tidal flats, we can walk across the tidal flats, we can do measurements, and Diana knows this very well. So we have access to those structures, we know how they form, and then we can compare the modern ones with the structures we find in fossil tidal flats as well. So it can be done very easily. And indeed, if we study the fossil record, and I get back to that in a moment once more, we see that MISS occurs since 3.2 billion years, and they have not really changed in morphology or facies-related distribution. Actually, this is 3.48, it's a little bit older. So in my talk, I would like to introduce some main groups of microbially induced sedimentary structures. I like to explain a little bit why they are important, and I like to show some very nicely preserved examples. Then I would like to show how benthic cyanobacteria form biofilms and how they grow up to microbial mats. And I like to do that with the example of modern tidal environments. Based on that, I like to talk about the interaction of benthic cyanobacteria with physical sediment dynamics. So how do cyanobacteria respond to erosion, to deposition, and so forth? And how do MISS form as a result of that interaction? And then finally, I like to talk about fossil MISS. We have wonderful preserved examples in the 2.9 billion year old Nagmasache section in the Pongola supergroup, South Africa. So let's take a look at some examples of MISS. So first of all, and you know that already, I'm sure Diana told you already, we are not at all talking about stromatolites. Stromatolites are build-ups that occur, that are being formed in a carbonate setting. I'm talking about clastic depositional environments where we have MISS. So here are a few examples. Here you see multi-directed ripple marks. This is a photo obtained from a modern tidal flats, and you see ripple marks. So here, ripple marks here and here, but you see that the surface is covered by ripple marks of different directions. Those ripple marks here run into this direction here and here and here, but here you see ripple marks that run into a different direction, which is from left to right, and here as well. This photo here shows a fossil surface which is covered by fossil ripple marks that show a very similar pattern. So here you have ripple marks running into this direction here, and here you have ripple marks running from up to down a little bit, and here ripple marks that actually have a direction of this here. So that's an example for multi-directed ripple marks. Polygonal oscillation cracks is another MISS. Here That is a modern microbial mat here. The scale is about 25 centimeters. And you see here a polygon here. This is another one here. Here's another polygon. And those polygons are separated by cracks that you see here. Here's a crack, this is a crack, here's a crack here, here's another one, and so forth. What is typical for those cracks is that they are overgrown by microbial mats, so you do not really see them. And we also see that each polygon has a margin which is kind of elevated. You see this, those are like, it looks like a rim here that looks like a sausage. So this is an elevated rim. So that means that each crack is defined by a rim here and a depression in between. Now that is what we see here in this fossil example as well. Here is a polygon. Here is a polygon. Here's another one, and here, and you see that those polygonal oscillation cracks are defined by two rims that you see quite nicely here because there's a different color. So here's a rim, and here is the crack in between. Multi-directed ripple marks formed by microbial mat that establishes on a sedimentary surface in the spring, and then it grows, it covers ripple marks. However, with the incoming fall, storms start to interrupt the microbial mat growth, and in the end, towards the end of the fall, we have a ripple mark pattern rising from this interaction between the growth of microbial mats and episodic storm events. Polygonal oscillation cracks are very typical for semi-arid climate zones, meaning in the summer and fall, microbial mats grow, but then they desiccate also because it's getting very dry, so they crack. So we have desiccation, cracks forming in the microbial mat, but then those cracks are overgrown again by the microbial mat as soon as the season becomes moist again. So if we have a repetitive pattern of desiccation and moisturing of the microbial mat, we get this typical polygonal oscillation crack. So there's an oscillation that we can observe. Those mat patches shrink, they expand, they shrink, they expand, and so forth. And that's the reason for the name. Erosional remnants and pockets. Diana told me she talked about those already in the course. So here a view into the tidal flats of the North Sea. Those are very big tidal flats, very similar like those that Diana works in. Here's a scale, 1 meter, and you see that the surface here is arranged into two geomorphological elements. Elevated surface portions that you see here, they are overgrown by microbial mat and they are planar, they are flat in appearance. And then there are depressions that you see here. Those depressions are filled by water here in this photo. Those depressions, there is no microbial mat and we can see ripple marks. This here is a photo from the Cretaceous Dakota sandstone that Diana also mentioned already. That's here in Colorado in the USA. Here you see a fossil microbial mat. It's planar. Here, that's all a fossil microbial mat. But here it was eroded away. So we see the sand, which was originally beneath the microbial mat, and the sand is rippled because currents were crossing the microbial mat and were eroding here and were put ripple marks into the sand. Microbial mat chips, very simple, are centimeter scale fragments of microbial mat that are distributed at random on a tidal flat. And here a nice fossil example from the Pongola supergroup, by the way, where we see very similar fragments of microbial mat. So there are a lot of other MISS, but I just wanted to show you a few examples to demonstrate that actually the MISS are really no stromatolites. They look different and they occur in clastic deposits. Now this here is a diagram that is a little bit out of date, but it shows basically where MISS occur with respect to the environment and with respect to time. So we know the oldest MISS occur in the Precambrian. We know them in the meantime from the early Archean, the oldest ones being 3.48 billion years old. They are in the Pilbara block in Australia. But the MISS occur through the entire Earth history until the modern time. They are very well known from tidal flats, from lagoons. We know them here from the Carboniferous and Permian in the meantime as well. I just didn't add it on yet. They're very well known from shelf settings. If you think of wrinkle structures occur in shelf settings. Predominantly, but we know MISS in the meantime also from fluvial settings and around lakes. So they are really very abundant and show actually a higher abundancy than stromatolites. Now, how do cyanobacteria colonize tidal flats? What do they do in order to establish and to grow microbial mats? So I must not really explain what a tidal flat is, but I like still to point out. So this is a photo of a modern tidal flat here in Virginia in the USA. We know, of course, there's the subtidal area that is constantly covered by water because it's below the low water line. Then there is the supratidal area, which is the area that is mostly dry. It might be flooded episodically during really strong storms like a hurricane, but normally the supratidal is dry. It's above the high water line. And then there is the intertidal zone. And the intertidal zone is actually the important area for a tidal flat. That is the area which is flooded every day, maybe every 6 hours, every 8 hours, every 12 hours by water. That is basically the area which is affected by the tidal current, the flood current and the ebb current. So that is the stage where we now take a look at our cyanobacteria. So first, like a long time ago, 25 years ago, when I was younger, people thought, geologists thought, well, if we see a sandy sediment in the tidal flat or wherever, the sediment is composed only of grains. Yeah, this is all quartz grain out there. There might be some polychaetes and clams and so forth, but that's it. And it took a while until geologists realized, well, those sands are actually colonized by microscopic organisms, by diatoms, by fungi, by cyanobacteria and other microbial groups. So that was kind of new to the real geologists, to really go ahead and to take a look at microorganisms. And so here are two examples of microbes that are very common in tidal flats worldwide. One is Merismopedia punctata, which here you see a photo. It's an organism that forms pillow-like clusters. The individual cells are round-shaped, they're coccoid. This one here is Microcoleus tonoplastis, which is a filamentous organism that is actually the one responsible why cyanobacteria earlier were called blue algae or blue-green algae, because people thought cyanobacteria are algae because Microcoleus tonoplastis is very big. You can see it. It looks like a little thread. Until in the 76, people realized, no, those are not algae, those are actually cyanobacteria. Now those names, Microcoleus tonoplastis, Merismopedia punctata, they're a little bit outdated, but they're still in use by people who work on traditional microbial mats in marine settings. So initially, cyanobacteria form biofilms around sedimentary grains. So here you see the surface of a quartz grain in scanning electron microscope. You see that this quartz grain is enveloped completely by an organic film. That's this here. That's what we call biofilm. And here you see a little diatom. Here's some other stuff in there as well. So biofilms are the individual cells of microorganisms plus the mucilages that they secrete, the extracellular polymeric substances, which we abbreviate as EPS, or simply slime. So if biofilms establish at sites that are very favorable for growth, they continue to grow. They become bigger and bigger and bigger until those biofilms cover large areas of sedimentary surfaces, and then we call them microbial mat. A microbial mat is the same like a biofilm. It's just a very, very big biofilm. Here you have a knife for scale. It's about 12 centimeters. And you see how coherent microbial mats are. They're so coherent that you can bend down, you can lift the microbial mat up, and you can roll it up like a carpet. And you can put it on your shoulder and carry it away if you so wish. So very, very coherent, very large-scale biofilms. We have seen microbial mats in Tunisia that have square kilometers in size. So they are very, very big entities, much bigger than what we know of modern stromatolites, which are, smaller in scale, more boulder shaped. If we talk about the common stromatolites, they're not as big. Now, very clearly, if we have microbial mats like that forming in a marine environment, those microbial mats must affect physical sedimentary dynamics. Those microbial mats affect erosion. They influence the position of sediments. And that's what I'm going to talk about now. What exactly do cyanobacteria do when they are affected by sedimentary dynamics in a clastic system? So let's take a look at that. Interaction of cyanobacteria with physical sediment dynamics. Tidal flats are extreme environments. We all can agree on that. The sediments are affected periodically by tidal currents, and that means, although this is a marine environment, the sediment are exposed to the atmosphere regularly, every day. So a marine organism that lives here needs to be able to adjust to being flooded, to be being covered by water, but also to be exposed to the air, and it's very difficult for a marine organism to do that. And then there are episodic storms that rework the sediments. They disturb the sediment. They just grab it and whirl it all over the place and redeposit it. And again, benthic organisms must be able to deal with that. So tidal flats are extreme environments in many, many ways. So this is just a graph, a very, very oversimplified graph, where we see the upper intertidal and lower intertidal is affected by the daily tides, the flood current, ebb current, flood current, ebb current. Then we have the spring high tides. So every 2 weeks or so, we have a higher flood, and then we have episodic storm events. So overall, it's a very difficult environment to live in. One thing I need to mention, if we have subaerial exposure of sedimentary deposits, we have very high ranges in salinity. If this tidal flat is exposed in the summer to dry air and heat, the salinity in the sediment is very high. But think, the same day in the afternoon, there is a thunderstorm coming and it rains very suddenly. Rainwater is fresh water, and it reduces the salinity in the sediment within a minute, very fast, to very low salinity. So again, a marine organism has to deal with changes in osmotic pressure at an instant. And now imagine you are not macroscopic like a clam or a polychaete. Now imagine you are a microscopic organism. You are attached to one sand grain that is affected by tidal currents. You are affected by subaerial exposure to hot air and heat and high salinity that can change very quickly. So now you realize how difficult it is for marine microorganisms to live in a tidal flat. It's really an extreme environment. So how do cyanobacteria respond to the sedimentary dynamics in a setting like that? So here's a graph which looks really complicated, but it's actually not. Here you see an arrow that indicates increase of intensity of erosion, and it defines this erosion here. This arrow here shows increase of intensity of deposition, and it defines the field of deposition here. And this arrow here indicates an increase in latency. Latency means that's a time period where we have no erosion and no deposition, meaning the sedimentary surface is completely quiet. Nothing happens. It's very quiet. Those rectangles here show how cyanobacteria respond to specific dynamic conditions. And I like to start here with this one here, which is situated at this arrow here, which basically means what happens with a microbial mat that is growing on a sedimentary surface which is not affected by erosion and not affected by deposition. So what we can observe is two things. First of all, we see that a microbial mat fabrics is establishing. Here that is a close-up here. It's actually a thin section through a fossil microbial mat, but we see very nice how the filaments, those are the dark lines here, how the filaments interweave. They form a network. But how do they do that? So what happens is that cyanobacteria and other microorganisms accumulate at a certain area on the sedimentary surface, maybe where there are a high amount of nutrients. And then they communicate with each other. They make a decision who goes where to form a network. They actively move through the sediment. They form a network. And the aim is to form a biofilm where each element, each cyanobacterium, each microorganism is able to interact with the neighbors in order to interlock the metabolic activity so that each microorganism can contribute to the overall community, and it benefits from the community as well. This establishment of a microbial mat fabrics, we call that binding. Binding, that's what that is. We also observe growth, which we see here. Here you see ripple marks. That's a vertical section through sediment. Here you see ripple marks. Here that's a ripple crest, ripple valley. Here's another ripple valley. And you see that the ripple valley is filled in, it's overgrown by very thick microbial mat. That's done by growth. That's not binding, that is growth. So cells are replicating, mucilages are being formed, so the microbial mat becomes thicker. That's growth. So those two activities we can see if the sedimentary surface is very, very quiet during latencies. So different latencies cause different types of microbial mats. That's important. So here you see a transect from the lower intertidal zone. It crosses the upper intertidal zone, and then we reach the lower subtidal zone, and this is the dry land here. So it's a vertical section. Now, the lower intertidal zone is not exposed much subaerially because constantly waves and currents rework the lower intertidal, and that means that only biofilms can form. Here you see sedimentary grains, quartz grains, and in between the quartz grains, this green material, that's Merismopedia punctata. Those are cyanobacteria. They can form only biofilms around each individual sedimentary grain. That is, the reason is that the latencies in the lower intertidal zone are so short that the microbes have no time to migrate through the sediment to form a microbial mat. They cannot do it because the substrate is reworked constantly. It's never quiet enough. This changes in the upper intertidal zone. Up here, the flat current crosses the intertidal zone maybe every 6 hours, every 8 hours, or every 12 hours. In between, the sediment is not reworked. That means there's time enough for microorganisms to form their microbial mat network because the sediment is not disturbed. What we see in settings like that is the formation of endobenthic microbial mats. Endobenthic, because they live within the sediment. They are inside the sediment. So here you see ripple marks, but we see there is something colonizing the ripple marks like a very thin skin. Those endobenthic microbial mats live in the upper millimeter of the sediment. They are not living on the sediment. That is the case with the epibenthic microbial mats. Epibenthic meaning on top of the sediment. Those are microbial mats that we normally think of if we hear the word microbial mat, the algal mat. That's how they look like, and they occur in the lower supratidal zone, which is covered by water maybe every week or every 2 weeks. So the sediment stays calm for a very long time, and those really thick microbial mats can form. They are centimeters thick, they can be decimeters thick, and they are characterized by a planar surface. Yeah, it's an even surface. We do not see ripple marks here anymore. The microbial mat is too thick. So now what happens during erosion? What do cyanobacteria do if they are being crossed by a current or if wave action affects them? We can see biostabilization. Biostabilization is microbial sediment fixation, and that is shown here. This is a close-up, a lateral view onto a microbial mat. Here is the surface of the microbial mat. You see here's a sedimentary grain that is overgrown by biomass. This is the surface here. And here we take a look into how the microbial mat looks like. Now, you might think I'm not able to take a photo which is in focus. So you do not really see the filaments of the microorganisms. And the reason is that the microorganisms are situated inside those slimes, those mucilages. So those mucilages are like glass, and that's why we do not really see the filaments. Yeah, we just see some biomass here. Now, this arrow indicates a current that crosses that surface, and we can now imagine that this network of filaments that you see here and the cohesiveness of the mucilages prohibit that the current rips out sedimentary grains from the microbial mat. That's what we call biostabilization. We were able to measure biostabilization types with respect to effectivity, with respect to effectiveness, and we were able to show that epibentic microbial mats that cover sedimentary surfaces like a cloth protect the sedimentary grains against erosion by magnitudes of 12. That means if we cause a current that crosses the microbial mat, we have to produce currents of velocities of 1 meter, 60 centimeters per second before we can observe any erosion. So it's a very effective biostabilization that those microbial mats show in if they are epibentic. This biostabilization type here is typical for endobentic microbial mats. You see here the microorganisms live within the sediment. Here the sediment is being held together mostly by filaments, not so much by mucilages, and we have a biostabilization effect of 3 to 5 times higher compared to sterile sediment. Biostabilization type 3 is different. This is something we observe where the water is too turbulent for microbial mats to form. So what we observe is that biofilms, which you see here, little biofilms, grow around the individual grains, and they might bind several grains together. So they form mineral biotic aggregates, and those aggregates stay in suspension for a long time because the aggregates have lower specific whites compared to grains that are not overgrown by biofilms. They have a higher specific white, and that means they sink down quicker than those grains that are protected by biofilms. It's kind of a parachute effect. The aggregates stay long in suspension, and they might sink down if the water is very calm, and they colonize then the top of the sedimentary surface. And that is important because cyanobacteria are photoautotroph. That means by forming those clusters, they are not being buried. Once the cyanobacteria are down here somewhere, that would be lethal to them because the sunlight does not reach really, really deep into the sediment. So biostabilization, a response to erosion. What happens if a microbial mat is indeed covered by sediment? Now, sediment is being deposited onto a microbial mat. What we observe is baffling and trapping. This is a view onto the same microbial mat that you have just seen. But you see here, the filaments are oriented vertically. They reach upward into the supernatant seawater, where they comb out actively, in a way, sedimentary grains that rain down onto the mat surface. So what they do is that they comb out, they baffle and trap specifically fine-grained material, silt-sized material, and what the effect is, they clean the water. They make sure that anything that would block light is being deposited. And indeed, if we take a look at the sizes of grains within microbial mats, specifically in the lower subcortical zone, we see that the grain sizes are smaller than the grain sizes of the host sediment. So it's kind of a cleansing effect to make the water clean so that light can reach the microbial mat. So baffling and trapping. The microbes then overgrow those grains and incorporate them into the microbial mat fabrics. Also, what we see is if the microbial mat is very thick, like several centimeters thick, we see that the quartz grains channel light into deeper portions of the microbial mat, and that means cyanobacteria that are lower in the microbial mat fabrics, they still can receive light. That's also an effect of baffling and trapping. Now, all those microbial activities interact with erosion and deposition and quiet times where the sediment is not being affected, and the end result are MISS. And that's what you see here in this graph. Here you see different MISS, like for instance, oriented grains, crinkled laminae, roll-ups, PTs, shrinkage cracks. Here, multi-directed ripple marks, oscillation cracks, and so forth. So those are individual MISS. And the diagram simply shows the main agent that leads to the formation of MISS, like here, biostabilization, for instance, is the main agent that forms PTs and shrinkage cracks and gas domes and mat chips, whereas baffling and trapping forms mat layer bound small grains, mat layer bound heavy mineral enrichments, or we have binding, which leads to the formation of mat textures, which is very important, of course, or sinoidal structures, whereas growth is up here, you might not see it, growth here, forms, oriented grains, and so forth. Here in the center, this diagram shows different MISS that form by a combination of biostabilization, baffling, trapping, binding, and growth. So those are structures, MISS, that show that rise from an overlap of different microbial activities. So now I like to go into the fossil record. Now I like to show you how do MISS look like in a rock and what do they tell us about the paleo environment. Of course, they tell us there were microbial mats, but really it's not that much of a surprise. But MISS show more, we can learn more about the environment. And in order to do that, I take you to South Africa into the Nhlasatsha section in the Pongola supergroup, which has an age of 2.9 billion years. That's about Mesoarchean in age. It's a beautiful, beautiful setting. As you can see, those are sandstones here that record a fossil tidal flat. In the meantime, by the way, this outcrop is suggested as to become geopark of the Wit'em-Folosi River. And that's the Geological Society of South Africa that is working on that. So then it might become part of the geoheritage site of the Barberton Greenstone Belt and so forth. So hopefully this is working. So I will show you examples. So the Pongola tidal flat is equivalent to a modern tidal flat. There are about 600 fossil MISS that are in statistical analysis identical to modern MISS with respect to geometry and dimensions, so macroscopic. The fossil MISS show a meter scale distribution in the area with respect to the different tidal zones, very similar like in the modern. So if we have MISS, they form associations which are typical for the lower intertidal, the upper intertidal, the lower supratidal, and the upper supratidal zone. So we see that both in the Pongola, also in the modern. And if we do thin sections, we do close-ups, the fossil MISS show very similar matte fabrics like modern ones. So I'm going to show you that. So here we have examples for MISS from the upper intertidal zone. Here, remember, I showed you a photo of multi-directed ripple marks. That's from the North Sea coast here, modern. But here, that's an example from the Pongola supergroup where we have different ripple pattern overlap. And if we take a thin section, we take a look, we see there are endobenthic microbial mats in here. So fossil endobenthic microbial mats in the ancient upper intertidal zone. Here another example for endobenthic microbial mats. You've seen that photo here. It's a modern endobenthic microbial mat that forms little microbial mat chips here. Here's another one. Here you see the ripple marks that are exposed. You still see them here, of course. But here you see the same thing in the Pongola supergroup. Here you see ripple marks, and here you see clasts. And interestingly, those clasts include ripples. Here's a ripple crest and another ripple crest. Here's another one. Here's a class and here's a class. Those are clasts very similar like those here. That one's formed by rupture of an endobenthic microbial mat. So this is typical for the upper intertidal zone in the Pongola supergroup as well. Now we move upward into the lower supratidal area, which is overgrown by epibenthic microbial mats, really thick microbial mats that have a planar surface. So here, remember, I showed you that photo. Here in the modern, we see ripple marks here that are overgrown by very thick microbial mat, and they are so thick that the surface of the microbial mat is planar, it's even. That's what we see here too. Those are ripple marks here in the fossil ripple marks in the rock. And here you see a microbial mat patch that overgrew those ripples. It filled in the ripple valleys just here. That's the same like this here. And the surface of the microbial mat is planar, just like this one. So this is a fossil epibenthic microbial mat that documents growth of a microbial mat in a fossil lower subparietal zone. This here is a modern microbial mat. You see beautifully preserved the blue-green, not preserved. You see beautifully the chlorophyll that gives rise to the blue-green color of the microbial mat. That is the edge of the microbial mat. It's being eroded a little bit. It looks fringed. This is sand underneath the microbial mat. And here we see a little microbial mat fragment. Here's another fragment. This fragment here was originally situated here, but it was ripped off and deposited. And here's another one, a microbial mat chip, a microbial mat fragment. Here we see the same in the fossil in the Pongola. So here's a green microbial mat. It's planar, just like this one, an epibenthic microbial mat. This is the edge of the microbial mat. Here you see a microbial mat chip, just like this one. It's the same appearance here, and this is the sand, which you see here. It's just a sandstone. It's fossil. So fossil microbial mat, modern microbial mat. Fossil microbial mat chip, modern microbial mat chip. Here is a fossil microbial mat chip here, and here is a modern example, looks just the same. So if we take a look at this fossil microbial mat, we do a thin section, a vertical section. We see here in the fossil filaments. Those are fossil filaments here, but we also see grains, sedimentary grains, quartz grains that are part of the microbial mat fabrics. Those grains we call oriented grains. They occur within a mat fabrics. This here is a modern example here. You see here the black lines, those are the filaments of the microorganisms. This more light colored part here is the EPS, the mucilages. You see mucilages here as well, mucilages here, extracellular polymeric substances. But then you also see those quartz grains. Here's one, here's one, here's one. And that's exactly the same that we see in the fossil record as well. So modern microbial mat, fossil microbial mat in microscopic close-up. So conclusions. In equivalent tidal flats, the morphology of MISS and the distribution with respect to the tidal zone, like lower intertidal, upper intertidal, lower supratidal, is comparable between the Pongola and the modern. So nothing has changed since 2.9 billion years. Now that gets me back to my original hypothesis where I said, were cyanobacteria already around 2.9 billion years ago? Maybe, perhaps cyanobacteria are older, are 2.9, but if they are forming complicated microbial mat ecosystems already, and we know in the meantime of fossil MISS in the early Archean of the Pilbara block in the Dresser Formation in Australia. So perhaps cyanobacteria are much older than assumed commonly and were developed to high diversity at least 2.9 billion years ago. But 2.9, I'm very positive. Those are real cyanobacteria already. Whether they are older, we might actually never know. There are different indicators that show cyanobacteria might be older, but not everything falls into place. So that's a book that I wrote about that topic. If you are interested to learn more, you can read the book. You don't need to buy it, but you should read it. So everything I know is in that book. And thank you very much for your attention.
Thank you, Nora. If someone wants to start doing questions. Okay. Adriana, ¿qué son las Plata Lakes? One minute, Nora, I'm getting. Okay, yeah. Yes. So I have a question from Adriana. She's asking if it is possible to see the same kind of structures in playa lakes.
Yes, yeah, absolutely. So playa lakes are affected by dry and sometimes humid weather conditions. So a very typical structure for playa lakes are PTs. It's not TPs, it's PTs. I'm not responsible for that. So those are TPs that are overgrown by microbial mats. And if you see PTs, they form a polygonal pattern, and the where there normally would be cracks in a TP, the microbial mat forms centimeter scale cauliflower-like elevations. So PT is very typical for playa settings, but we've also seen, of course, microbial mat chips. We have seen roll-ups and other MISS as well.
Okay. Do they happen in margin lakes? Same question from the same person.
What are margin lakes?
Adriana, what are margin lakes? ¿Qué son los margin lakes? Well, in the meantime, everybody's thanking you, Nora. They're saying it was very clear.
Thank you.
Excellent. Okay, I have another question. Nora, what can you tell us about compactation and diagenesis?
Yeah. So microbial mats in clastic settings include a lot of sand grains. Even epibenthic microbial mats include a lot of sand grains. So compaction, as we know it from carbonate, doesn't really take place. So even if you would squeeze a fossil microbial, or you squeeze a microbial mat during diagenesis and lithification, there's almost no compaction unless you are able to compact quartz, which is very difficult to do. So we all know stylolites from limestone, carbonate rock. Carbonate rock you can compress. Calcite is not, dolomite you can compress. So there's recrystallization. You can do that with quartz as well, but then you have to do real high pressure tectonic, and of course, it's way higher than it's possible or it's necessary for carbonate. So compaction really in fossil MISS does not play much of a role. We have no change in morphology with respect to compaction. with respect to diagenesis, what's very important to understand is that in stromatolites, we have the mucilages, all the EPS is transforming into carbonate minerals. So aragonite, calcite, dolomite, siderite, whatever. That is what happens in stromatolites. That does not happen in MISS. But what we see in MISS is some silica forming, so chert forming where the EPS is, very little. But mostly what we see in our fossil MISS are the microorganisms themselves that are forming minerals, and we know it's a typical mineral association that we see again and again and again in the fossil, which is chemosite, pyrite, hematite. Now I would have to think. I said the chert, so silica. And I know I always forget at least one. So it's a typical association that we find in fossil MISS in the clastic record. And of course, if it's hematite, it you know, or if it was pyrite, it oxidizes into hematite or goethite, lepidocrocite, and so forth. So that's typical. But you will see if you study fossil stromatolites that very rarely ever you see the fossil filaments. That's typical for stromatolites. Many stromatolites, you do not see the microorganisms. But what you see is this abundant EPS that forms now the carbonate rock.
There is another question from Dr. Perillo. It says, in your presentation, you discussed the effects of tidal currents, but you did not mention wave activity. How much excess shear stress you need from waves in comparison with currents to move mats?
So that's an excellent question, because I say stromatolites are made by waves and MISS are made by currents. So if you take a look at the distribution of where stromatolites are and where MISS are, the stromatolites occur in deeper water. They have to. Think of a very common stromatolite, like the textbook stromatolite, which is an up-domed structure, right? A domed structure. That dome has to be underwater. And if you have water of a certain depth, you have waves. And also for carbonate minerals to precipitate, you need energy, right? For carbonate mineral precipitation, you need energy. And the energy is provided by the waves. For MISS, they occur higher up on the tidal flats in areas where the flat current is very shallow. But here comes now the trick that the microbial mats use. Because they do biostabilization. What they exactly do is they reduce the dynamic of the flow. So they change it from turbulent to laminar. That's exactly what they do. And that means even if there is a wave coming on and, oh, I'm now eroding that microbial mat, the microbial mat protects itself by reducing the turbulence into laminar flow. And as you know, laminar flow has not the erosive energy like turbulent water has. So that is the trick the microbial mats use.
I have another question from Agustin. He says, I am particularly interested in carbonate. Diana showed in her course that some carbonate laminae are formed within her microbial mats. Have you found authigenic carbonate related to the MISS of Pongola? And if yes, what can you tell us about their biogeochemical signals?
So I've not seen anything in the Pongola. We specifically looked, and the reason why we looked was because we know, and you know that much better than I do, in modern microbial mats, even in those microbial mats along the North Sea, which is a colder climate, it's raining a lot, I know that, I did field work there, even in the summer, cold, rainy. But those microbial mats, if the weather becomes better, even if it's just for 1 or 2 days, they form little dumbbells, the typical famous aragonite, dolomite, calcite dumbbells, which means that some carbonate precipitation takes place, but that's being dissolved as soon as the weather changes again very quickly. But the only area where I found a little bit of carbonate in MISS are the fossil microbial mats, the MISS in the Dresser Formation in the Pilbara in Australia. There's just a very little, otherwise not.
Good. I have a question for relating to modern settings here from Christian Pereira. He says, microbial mats, so far as I know, can be seen as bioengineered organisms, and they spread out along a wide area in the intertidal. Comparing that pattern with other bioengineers, such as crabs, from the same sector, many examples show that when the crab colonizes the microbial mat section, they destroy the mat. But prior to that, there is a segregation of space between them, between both the crab and the mats. Is there any distinct time period for the development of new mats that the crab can use to colonize the mat sector? For example, when the crab finishes molting, the mats are destroyed by burrowing by the crab?
We did not work on crabs, but we took a look at clams and polychaetes and so forth. In 2003, we had a very big hurricane here in Virginia. And it so happened that I studied a microbial mat site the week before the hurricane. And I took a look where the microbial mat is growing. We measured the biostabilization and all that. It was a fat and happy mat. Then the hurricane came. And so the week later, I went back to the same site to check on the microbial mat. And it was gone. It was eroded away completely. No mat. With one exception, there was a very small patch in one corner. So I took the opportunity and I went back to that site every 2 weeks until the winter started. And I was able to see that where there was endobenthos already, macroscopic organisms like clams, polychaetes, and so forth, where those organisms were able to colonize very quickly, the microbial mat would not grow. But where the microbial mat was faster to colonize the surface, it would block macroscopic organisms from going into the area. So as soon as you have an endobendic microbial mat, and it develops and very quickly into an epibendic microbial mat, the macroorganisms would not go into the microbial mat and destroy it. And quite honestly, I've never seen any macroscopic organism grazing a microbial mat or doing anything, so it would be destroyed. Now, it can be with the crabs, it's different, but that I really don't know.
Good. And I have one last question from Ricardo. He says, the pictures of modern analogs you were showing with 2 sets of different ripple patterns aren't related to spacing or larger order bed forms? And what are the explanation of the double-crested ripples in your interpretation?
So let me start with the multi-directed ripple marks. So here you see a fossil surface, and this is a modern one, right? So in order to study how those ripple marks form in the modern, let's start with that. I went to Malum Island in the North Sea, and I went every month for 2 years, every month. And I studied the ripple marks pattern in a certain area, and I realized that in the spring you have one ripple direction, and then the microbial mat starts to form, but the microbial mat does not migrate onto an area like a front like this. What the microbial mat does is it forms little patches. And those patches expand laterally over time. And that means wherever there's a microbial mat patch, a ripple mark direction was biostabilized. It could not be moved anymore. And so you have the first ripple direction is preserved under the first ripple patches. Then you have a second ripple direction preserved where the patch was expanding, and so forth and so forth. And we were able to show that the microbial mat community, the microorganisms, the maturity of the mat on certain ripple directions changed from a very young mat to a very old mat. So that specific ripple directions, let's say this one, this one, this one, they all had an old microbial mat community, whereas those microbial mats here, or those ripple marks here, here, had a young microbial mat community. So now I have to go into the fossil record and do the same here. We make sure that we investigate ripple marks of one and the same rock bed. That's very important. So the ripples that you see here, they all belong to one and the same surface, more or less. And then if we go ahead, and you don't see that quite honestly on this photo. Let me see whether I have a better one down here. Yeah, here you see it. See here. You see all those ripples are on one and the same surface. This here is a different rock bed. This is not. This is all the same. All the same. And if we go ahead now and take a thin section, we are able to show endobenthic microbial mats, epibenthic microbial mats. So different types of microbial mats that relate to a specific pattern of ripples in an area. So you can really see that. But again, and you were completely right, you have to be careful that you don't, in the fossil, investigate ripple marks that actually were formed 10,000 years later, or whatever time is recorded by the outcrop.
I concur with you, and also from a biological perspective, I'm a biologist. There is like a mosaic pattern in our tidal flats, in which not only we see different MISS, modern ones, but also if you go down and study them from a microbiology point of view, there's different communities or different proportions of different cyanobacteria types within them. So I concur with what you just said. I don't know if there's any more questions coming up. That was the last one for now. Yeah, okay. I thought Dr. Perillo was typing, but apparently not. All right. Well, that should be it for now. Diana, do you want to close it, the talk? Yes. Thank you very much, Nora, for your talk. It was very interesting.
Yep, my pleasure.
And super clear. As
and nice questions. Thank you.
It was an excellent conference, Nora, and as
as always, we learn a lot with your conference, with your papers, and with your work, because it is very, very nice to read it. So we learn a lot with your results. Thank you very much.
Yeah, thank you for the invitation. It was a lot of fun.
Well, thank you. Bye.
Bye-bye.
Thanks, bye.
We can stay.
Diana, creo que tenés que dejar de grabar. No sé.